नहीं, मस्त टीम तो अच्छी निकाली है सर। तेजस इन लोगों ने काफ़ी हेल्प की थी एसएच के टाइम मुझे। जो इंटरनल हैकेथॉन मतलब एसएच वालों का इंटरनल लेवल पे लिया था ना हम लोगों ने, दैट टाइम इनकी पूरी टीम ने बहुत हेल्प किया था मुझे।
अच्छा। गुड। टाइम है। लोग ज्वाइन कहाँ होते हैं 5 बजे बगैर? 5 बजे के बाद ही ज्वाइन होते हैं सर।
सर और कल के लिए भी हम लोग एक ओवरऑल फीडबैक लेते हैं ना, उसका फॉर्मेट अलग होता है क्या, या फिर कौन बनाने वाला है?
यू डोंट हैव दैट?
नहीं, मेरे पास नहीं है वो
एक
ओवरऑल।
एक
शायद
काम
निखत ने डाला था शायद एक बार। तो
यस यस, यू गिव ए कॉल। FDP2 का फॉर्मेट होगा सेम, इट इज सेम, ओनली डेट्स एंड दिस हैज टू बी चेंज्ड।
ठीक है, आई विल चेंज दैट एंड वो ग्रुप पे मैं
दैट्स इट,
डाल देती
दैट्स
हूँ,
इट।
अपने CWC के ग्रुप पे डाल देती हूँ, सो दैट एनीवन कैन शेयर दैट लिंक।
Rithvika also joined. Good evening, Rithvika.
Good evening, sir. How are you doing?
Yeah, fine, fine. Soumya, good evening.
Good evening, sir.
आप लोग हमारा एंड कर रहे हो FDP का, पता है क्या, ट्रेनिंग प्रोग्राम का?
Uh,
तो
really
तो
nice
समझ,
that we can come and present. It feels
Yeah,
really
yeah.
good.
Thank you so much.
Thank you for inviting us.
वेलकम, मोस्ट वेलकम, सिंसियर बच्चे आप लोग। गुड इवनिंग आरती मैडम।
Good evening, sir.
गुड इवनिंग। Kalmande sir, good evening.
Sir, good evening, good evening. Good evening, sir, good evening.
Good evening.
आवाज ऐकू येतो ना? आवाज येतो का हो ऐकू सर?
यस सर आ रहा है.
सर तुमचा आवाज पूर्ण S.P.I.T मध्ये घुमतो.
आता जस्ट चहा पिऊन आलो बुवा.
हा बरं आहे. एकटे घ्या आता चहा.
Good evening, Kalwandi sir.
We will take a tea in the next week, sir,
Okay.
in college.
Yes. निर्भय सर आ गए. डॉक्टर निर्भय सर, मोस्ट सिंसियर स्टूडेंट. चौबे साहब नमस्कार. मैं भी ऑन नहीं सर. Harshil sir, shall we start?
Yes sir, I'm ready.
We will ask to Rithvika also. Tejas, Rithvika, are you ready? Shall we go ahead?
Yes, sure, sir. Ready.
Yeah. People will keep on joining. We will do our job. We'll start. Okay. So
Okay.
Harshil,
Yes, sir.
go ahead.
Good evening everyone. I Harshil Kanakya welcome you all to AICT sponsored FDP on Insights into Intelligent Automation, Machine Learning, Data Science and its application. It is my privilege to introduce today's speakers, Mr. Tejas Chheda, Ms. Rithvika Iyer, and Ms. Soumya Koppaka. Mr. Tejas Chheda is Artificial Intelligence Engineer at Miko. He is an incoming student for Masters in Computer Science. His interests lie in the areas of software development and machine learning and its application to various sectors, including healthcare. He did undergraduate in computer engineering from Sardar Patel Institute of Technology, Mumbai. He has worked on natural language processing projects at Miko, an advanced robotics AI startup, and Ogum, a leading next-generation data analytics company in the professional capacity. At Skinsy Software Solutions, he worked on skin disease prediction from images and gained experience in building computer vision-based application. He also worked as a research intern at IIT Bombay for the project Social Media Sentiment Analysis for Hindi language. Additionally, he has developed multiple applications that are published on Google Play Store. Welcome, Mr. Tejas. Ms. Rithvika Iyer is a data scientist at Reliance Jio. She has done bachelor's degree from Sardar Patel Institute of Technology, Mumbai. She was machine learning research intern in IIT Bombay. She worked as machine learning software developer in Skinsy Software Solutions Private Limited. She is awarded Best Engineering Student of Mumbai 2020. She was a winner Smart India Hackathon in 2019 and won the Innovation at the Smart India Hackathon 2018 for the project aimed at stakeholder engagement in smart cities. Ms. Soumya Koppaka is graduate engineering trainee at Piramal Pharma Limited. She has completed computer engineering from Sardar Patel Institute of Technology, Mumbai. She has an interest in technology, including the latest trends and possibilities. She likes to develop new technologies using artificial intelligence. She is in the winning team of Smart India Hackathon 2019. Welcome, Ms. Soumya. They are going to deliver a session on anomaly detection methods for endoscopic videos. Over to you.
Yes, thank you so much for the introduction. I want to thank Rathod sir for having us. We feel very honored to come and present in front of such an incredible audience. So today's session, we would like to speak about a project we worked on, which uses data science and has applications in that field. Yeah, we can share the presentation.
Can you see my screen? Can you see the presentation?
Yes, we can see.
Okay. Should I start?
Yeah, sure.
Oh, it's not visible. One second.
Can you see the presentation or should I reshare?
I can see the presentation.
Oh,
Okay.
I'm not able to. Okay, it's okay. I have the presentation with me, so I will. Okay. Okay, so I'll start. One second. Should I? Why is it not visible?
Okay. Soumya, should I? Yes, sir.
Yeah,
Rithvika,
just start. Just start.
it is visible to us. We can hear you clearly, and PPT also very visible.
Okay.
Yeah.
So, Soumya, could you just rejoin? I'll start.
Yeah. Sure.
Sure. All right. Good evening, everyone. Our topic for today is gastrointestinal tract anomaly detection from endoscopic videos using object detection approach. So, we'll do a deep dive into all the components of this very long heading. So, let's start. Yeah. So, our first question for today: what really is endoscopy, right? Endoscopy is, I think most of us are familiar with it. It's a minimally invasive, it's a non surgical procedure that is used for two reasons. One, to detect anomalies that are present inside our internal organs, as well as to perform certain minor surgical procedures. Right? So, and it's used for therapeutic purposes, and we all know it in the context of biopsies for cancer detection, etc., where a small section of like our internal organs is taken out and then sent to the lab for further diagnosis. So we have various types of endoscopies. We have depending on which internal organ that it is examining. So the esophagoscopy, which is of the esophagus, the windpipe; gastroscopy, which is the entire GI tract, the stomach, the small intestine, the large intestine; colonoscopy, which is the colon, large part of the large intestine; the ERCP, pancreas; and laparoscopy, which is very specifically abdomen and pelvis. Moving on. Soumya, when you're back on this thing, do tell me, all right?
Yeah.
You can
So
see.
sorry.
Can you see?
No, it's not visible.
Okay.
I'll try it once again. Yeah, continue.
All right. So, what really is the major problem that we face with endoscopy today? The number of specialists that are present in a country like India are extremely few, and they're mostly concentrated in the developed cities and hospitals, etc. And so, therefore, and this procedure is entirely dependent on very specialized knowledge of the doctor, which is why even if an endoscopic procedure is performed in rural areas, there is nobody to analyze it. These video streams are analyzed live on a screen, and they detect anomalies, and they say that okay, this is how you should go ahead, or this is what you should do. We need a further scan, etc. So what we recognized is this paucity or this need where you know to create something that can aid in the process of anomaly detection in endoscopic videos itself, to do two things broadly: annotate and analyze these videos. So the scope of this, once we started working on it, we realized is not just for endoscopy but for other medical procedures as well, right? And if we collect all of these live stream videos, we analyze it, we do we annotate it well, then this can be used as like a learning tool for medical students all across the country. So essentially what I'm setting is like some sort of a background, an introduction as to why we took up this project, and then we'll do like a deep dive into what exactly we did to create this product from end to end, this project, right? So I think I've convinced you about the social value of this project and the huge impact that it can have. So this is essentially how we will break our entire material down. So we'll do a literature survey quickly. We have a background as to what disease. Yeah.
I can see now.
All right.
I can take
over to you, Soumya.
Yeah, I'll begin the literature survey. Hello, am I audible?
Yes, go ahead.
Yeah, so basically, our literature survey. Oh, echoing. Is it still echoing?
No, we can hear you well.
Okay, so the literature survey is divided into 3 parts. The first part is object detection. So in object detection, we have surveyed 3 main methods or algorithms. First one being YOLO, which is you only look once, which is a single stage object detection algorithm. The second one is RCNN. It's a customized neural network. The third one is called one-shot multi-box, which is a one-stage object detection algorithm. So I'll be explaining each algorithm in detail in the following slides. The second part of our literature survey is video annotation. So in video annotation, since it's a medical field, we have to annotate accurately parts of the body because it's very critical. So this is also a very important area of research. The third part, obviously, anomaly detection. So since we are endoscopies are basically performed to detect various anomalies and check and analyze a particular body part. Anomaly detection is also very, very crucial. Yeah, we move on to object detection. So in object detection, various research methods have been carried out. I think one of the foremost parts in a frame is the separation between the foreground and the background, because only then will you be able to accurately detect the boundary of an object. So there has been research done where they're separating the foreground and the background based on the pixel values of the difference in the pixel values between two adjacent things. So that's how they calculate the separation. The second thing is the foreground is also calculated. Foreground as an object in a particular frame are also found out by calculating the change of that object with respect to its surroundings. So that's how we obtain a boundary. So we check the difference of pixel value between two concurrent or adjacent frames, and then we measure the number of pixel values that. Similarly, we can also check which pixel values are stationary in all of the frames. So generally, the background is constant. When we take frames, like say at 1/40th of a second, then the background will be more or less constant. So those pixel values won't change. So through that also we can calculate the background. Another method is using the YCP-CR color space. So how is this different from the RGB color space? The YCP-CR color space does not use direct color of values. It measures the intensity and the difference between the blue pixels and R pixels. So that's how they can be used to detect skin or some particular color using the range of that value and then setting a threshold. Yeah. Another method which uses AlexNet. So AlexNet,
Soumya,
yes,
your voice is breaking.
it still breaks.
Yeah.
1 second. Is it better now?
Yes.
Yes.
I
Okay,
think
okay.
so. You continue. I think it is better now.
Okay, okay. So yeah, the second is AlexNet based. So AlexNet is basically an architecture which is used for object detection. So this is basically an 8-layer deep neural network, and it has already been pre-trained using a image data set which has over 1 million images and 1,000 classes. So if the network can already predict 1,000 different types of objects, like animals, house, keyboard, mouse, pencil, so this has already been trained, so we can directly use it for object detection. So it is one of the most used architectures out there. Again, it is 8 layers deep. So this is one of the most commonly used object detection algorithms out there. What it does, firstly, you identify key frames in a video sequence, and those frames are then passed on to the neural network, which has already been trained using the AlexNet ImageNet dataset. And then they track changes in the pixel values over adjacent frames and then localize a particular object. And since it has already been trained, it will accurately recognize the object as well and give us a probability value. Next. So this is the algorithm that we have used in our research, something that worked for our scenario. It's called YOLO, you only look once. It was introduced in 2015. It is a single stage model. Basically, in a single stage model, the object is detected in one go. Whereas in a two stage model, the first stage the object is detected, and in the second stage, a boundary is created. So in this stage, the object is detected directly using bounding boxes, and below the bounding boxes there will be a class predictor with the value of the probability of the prediction. But the drawback of YOLO is, even though it is faster, the accuracy is slightly lower because it's a one-stage model. And it has also been applied before to detect polyps from endoscopic videos. It works in our scenario because we require a faster model and more real time. Since the doctor, while performing an endoscopy, needs to see the objects detected and anomalies detected. Yeah. Another one, it's called another two-stage algorithm, RCNN, is a neural network. So this model is two-stage, hence it uses feature extraction and classification. In this model, it takes all the possible bounding boxes to make localized predictions, unlike YOLO, where it just considers bounding boxes above a threshold. The RCNN gives us a much higher accuracy, but it is quite slower because the model is very extensive. There have been newer and faster variations of RCNN too, but they are still quite delayed and won't give us as real-time predictions as compared to YOLO. Yeah. Another part of our research survey was annotation and analysis of the endoscopic video. Now, once we have detected objects in the video, we have to annotate them accurately as well. Now, annotation is accurate because in endoscopic videos, we need to localize a particular region. So the various steps in video processing, we start with video summarization. We can't use all of the frames and process them because that will make the processing expensive and the results won't be as real time and fast. So we need to eliminate non-informative or similar frames. So we compare two consecutive frames, and if there isn't much difference in the pixel values or the number of pixel values changing are very few, then we can discard them. That's how we summarize the number of frames. Pre-processing. So there are various pre-processing image pre-processing steps that can take place. They can be image enhancement, reducing the noise of an image, correction, distortion, or removing distortion in some way to improve the accuracy of the prediction. We also have diagnostic in any way if we can improve the image. After this, segmentation. Segmentation is basically separation of different parts of the image. For example, foreground and background, that will also be one sort of segmentation. And we use pixels to localize organs and anomalies in our case. Followed by feature extraction. Now we do feature extraction because we want to feed the feature vectors which we get from feature extraction into our neural network. So it is able to detect which type of anomaly it is. And for classification, there are various algorithms like the support vector machine, which gives us, which predicts which class the image falls into. And multi-layer perceptron is another way to classify frames. Yeah. Yeah. So some of the methods that have been that work has been done in the past includes for video annotation, one of the most common and highly used is the convolution neural networks. It is very accurate and gives us good results as well. There's also a kernel density estimation. A kernel density estimation is basically an algorithm to estimate the probability density function. So what it does is, basically smooths the data, gives us a better, more accurate image by eliminating noise as such. So basically, it will calculate the density of the image and then smooth it and remove any noise. There's also Gaussian mixture model. Now, Gaussian mixture model is also similar to the KDE. What it does is uses multiple methods. It uses a probabilistic approach to calculate the probability of subpopulation. Now, subpopulation in our case will be smaller objects detected in an image. Then we also have hidden Markov model. Hidden Markov model also uses this, but it uses hidden weights. So it will calculate weights that you wouldn't necessarily know, but they are important to detect an object. There's also wavelet decomposition, which is a relatively newer approach that they have tried, which they have used filters as wavelet decomposition basically filters an image to get one particular part of the image, and then it's LDA is performed to get the feature for the same. Other than that, there are other aspects to endoscopy also where technology has been used. Firstly, the 3D reconstruction of internal organs. You may have seen in movies or in TV shows that they reconstruct an internal organ using multiple angle images. So basically what it does is, using the images taken by an endoscope from different angles, we are able to put together those images and give you a 3D reconstruction. This is of immense help to the doctors as well. But this is again nascent stages of development. There is also wireless multi-screen detection using analog signals. Now, not all regions performing endoscopies will have access to high-end machinery and good quality cameras and all of that. So there is a way to convert these signals into analog and read them as well. So that is also being worked on using ARM processors. Yeah. Now, anomaly detection, of course, it's one of the most important parts of the research. Um, Even if we are able to detect objects, organs, or some sort of anomalies in the frame, we need to be able to tell what kind of anomaly it is. This is very critical because we cannot we cannot miss detecting cancer or wrongly detect cancer. uh, it can be critical to somebody's life as well. So it's very important that this part of the research is accurately done. So there have been various anomaly detection algorithms working with different anomalies, including polyps, cancer, inflammation in cells, esophagitis. Um, so what we are doing in anomaly detection basically is we are extracting feature vectors from the frame for each anomaly and then training the deep learning model for each of them. So we have, say, pre-trained a data set for cancer cells, and we train the model using those data sets, which are already annotated or can be annotated. And these frames, again, can be trained using various different algorithms. Yeah. Now, for feature detection, again, there are various methods that are being used. I'll start with LBP. LBP, or local binary pattern. So this is an algorithm which detects features based on their pixel value. So for each pixel, the value is calculated on the basis of the adjacent 8 neighboring pixels. And using all of those pixel values, we construct a histogram, and that histogram is passed as a feature vector to the later algorithms. Similarly, for histogram of oriented gradients, here what we do, it's similar. It's used for feature extraction only, but here you count the number of gradient orientations in the image. So you are taking the difference between two pixel values and making it into a histogram and then passing it into feature vector. Again, we also perform color texture analysis because there are certain anomalies which are just a particular color or have a particular texture. So if we can detect just that, then it will also be an important feature. There is also principal component analysis. And we have scale invariant feature transform. Scale invariant feature transform will work. It basically gives you the same values even if the image is rotated or has some other is increasing, has a bigger size. So all of that will not matter if you use SIFT. It will still give you the same feature vector for the similar anomaly. Yeah. And then the next step after we pre-process the videos is to classify or predict which anomaly it is. And for this, we use either SVM classifier or random forest classification algorithm, multi-layer perceptron, or train your own supervised convolution neural network. Training your own neural network is something that is being used most extensively because we can personalize whatever we want to do. We can change the hyperparameters on our own, use our own data set to train it. So yeah, that will be the most accurate and give the best results. Next. So these are the two data sets that we considered while we did our research and for training our algorithm. The first one, the endo-abs dataset or the endoscopic abdominal stereo images dataset. These also allow for 3D reconstruction, which we did not really work on, but it gives us images of all the organs, over 120 images of each organ and its ground truth. We also use the Quasar dataset. Now, the Quasar dataset is mainly used for anomaly detection. It comes with 8 anomalies, including polyps, esophagitis, etc. And each anomaly has 1,000 images in each class, basically. And this dataset is annotated and verified by medical professionals. And it is specific to gastrointestinal tract anomalies, which is our main focus. Next. So I'll just summarize. Since we have used an object detection approach, there are a few main algorithms. Single stage, which can be YOLO and SSD, or the single shot multi-box detector. Two-stage approaches, including RCNN, faster RCNN. RCNN, what it does, it's a two-stage method, so it's much slower, but it gives you a better classification accuracy. The fast RCNN and faster RCNN, even though they are better with accuracy, they are still not fast enough as compared to YOLO. We found YOLO the most appropriate for our research is because it consists of a single neural network, and it gave us the predictions much faster, even though it was not as accurate as RCNN. And it didn't require as much computation as well. So it was suitable for this application. Yeah.
Right. Thanks, Soumya. So I'll take over the next part. So before we get into the background and how exactly get into the details of our model and the results, etc. So let's zoom out a bit. What really are we doing over here? What we're doing is that we're taking an example of annotation of endoscopic videos to explain basically any object detection task. What does this task involve? Why do we do it? How do we do it? And what is the way to evaluate what we've done? Right. So after I cover my part, which is essentially giving you a background of the specific task that we've taken and the specifics of the model architecture, etc., we'll give you a demo of how exactly it works, how it looks. After which, Tejas will run you through the results and how we've evaluated them and improved upon them in versions. And finally, we'll have a code walkthrough, right? So let's get started. So we've covered what is gastrointestinal endoscopy, right? We've covered all the types of endoscopy. So we are going to be dealing specifically with anomalies in the GI tract. We have selected 2 anomalies, there being esophagitis and polyps. Esophagitis is essentially the inflammation of the esophagus, right? And it has red and white striations on an otherwise normal esophagus. And this is caused by gastric acid reflux, which is acid coming back in from the stomach. And the second anomaly is polyps, which is like a protrusion that comes up on the colon wall. What is the reason for selecting just these 2 kinds of anomalies? Because they represent 2 different challenges to the whole object detection problem. The first one being polyps, which are relatively well-defined mucosal outgrowths localized to a particular region, and esophagitis, which is a very irregular anomaly that is spread across a large region. So we wanted to see how well our model could generalize to both these and therefore could be scaled across multiple such anomalies in the future. Right, so this is a visual representation of how the anomalies really look. So the first one, you can see polyps. This is essentially the polyp, which is the protrusion on the wall that I was talking about. And this is esophagitis, where you can see that the red striations that occur on the wall are the regions where the wall has gotten corroded by the acid. Right. So let's do a deep dive into. So Soumya took us through the entire literature survey. The literature survey was divided into 3 parts. The first one being object detection, given that we wanted to see what is the research out there with regards to object detection, what are the various differences between them. Second, our main task, which was anomaly detection itself. What are the ways that are currently being used to detect anomaly? And in that, we found the primary of them being convolutional neural nets, traditional image processing techniques, there is S.I.F.T, there is color imaging, all those kinds of things. And the third part, which is how to process videos in the best way possible and extract most information and assimilate them into features that we can then use for further analysis. So these were the 3 parts of our literature survey. These are the primary gaps that we have identified with regards to literature survey, which we have then taken forward and converted into a project. So the first thing that hits you is that when it comes to anomaly detection in the whole healthcare space, specifically to endoscopic videos, there is really no application out there that uses object detection methods. At best, there are deep learning classification algorithms which are not able to do as good a job as we believe that object detection will do. Primarily because object detection does a combination of 2 things, not just classify the anomaly, but also localize it to a particular region, right? Our second gap identified is that we need real-time results, right? We don't have to pass something through another model later on and get a classification which may or may not be correct. We need something in real time because that is how an endoscopic stream operates, right? Then coming to object classification itself, technical details inside it is that when the image is distorted, when there is noise, when there is not much distinction between foreground and background, when the features are not able to be extracted very well, then our results are not very good. With regards to the video section, it's very difficult to maintain camera clarity, focus. These are problems that are probably being solved all over the world in various ways, and it was our humble attempt to bring all these problems forward and try and take each one and solve them in a particular way, right? And another interesting thing that we did is we took data from all possible angles so that it is inconsistent in terms of the light, in terms of the angle, in terms of all of that, and still see how the prediction is being performed. And the final and last thing, which is one of the major problems in data science today, is that extensive computation is required, which is not going to be handled by normal CPUs, and we need to reduce the time of prediction of our very heavy models, right? So then this is a summary of the gaps identified and the corresponding research contribution of our project, right? So we said that only traditional image processing applications were being used for anomaly detection. What we're trying to do is to use object detection to classify and localize the anomaly. So so another thing is that this will serve as a prototype for tomorrow various other projects that people can take up in terms of an end-to-end pipeline for video processing to frame extraction to anomaly detection, whether be it a deep learning or an object detection approach, to finally annotation as well as analysis, and then the doctor can draw insights from that, or even a lay person can draw insights from that. And our third, which is a very technical contribution that we believe we've made, is that we have proved in a way that we do not have accurate metrics. The current metrics for evaluation of these object detection models is not very good. And we will show you the difference between the visual results and the actual metrics that we get, and how we need to develop a better system to evaluate model performance. So moving on to our next section is, let's actually, this is more of a section where we explain, one entire object detection architecture and what goes on in the back end to actually seeing the localization as well as classification. So what really is object detection? I think all of us have used these buzzwords of convolutional neural networks, which, the very famous cat-dog classification problem, wherein you pass a data set, you train your model to learn the difference between two different types of images, and then you pass a new test image, and it's able to tell you that, okay, it belongs to class A or it belongs to class B, right? So what does object detection do? Is it does what I have just described above. Yes, it classifies it into a particular class, but it also tells you in that particular image where that object really is. So that's what it manages to learn and tell you, right? So it's a combination of these two things that we are going to be using. I kept using the word annotation. Annotation really is, as you can see over here, the bounding box that is created around the object belonging to a particular class in the entire image. So I am localizing that this is where the cat is in this image. All right. And for example, if there is no cat in the image at all, there will be no bounding box that will be created, which brings us to a very big advantage as to why we're using this method at all over and above traditional image processing or deep learning methods, right? So yeah, this is essentially how it happens. You have the image, which goes in for convolutional and pooling. You have the FC layers. So you generate your box coordinates, which is your x, your y, your width, and your height, right? And then, so you have bounding boxes that are generated. Then you have what you also get is your scores for a probability of belonging to a particular class for each x, y, wh that is generated, which then tells you that, okay, this probability of this belonging to the cat class is, say, 0.8, and belonging to the dog is 0.7, which is how you segregate. And we'll see later how we're actually measuring that. But this is essentially what object detection really involves. Coming to our model, the YOLO version 3. You only look once. Soumya told us earlier why we're using this. We're using this primarily because it's one of the state-of-the-art architectures when it comes to object detection models out there. One of the primary advantages of the YOLO model is that it gives a very fast speed of prediction, which is essential because what we want to do is a real-time annotation of the endoscopic video itself. As the endoscope is going inside the body, we want the frames to be annotated and relayed on the screen so that we do not miss even a small anomaly in any part. So speed is essential for us, right? I will now explain to you what the architecture, what goes on inside a YOLO version 3 in a very simplistic format. So this basic block diagram explains what is an object detection model really. You have images coming in and you have two primary parts. The first one being the feature extractor. So today, if I ask you, what is it that makes you recognize something out there as a boy or a girl? You have certain things in mind, right? A girl usually has long hair. A boy has short hair. A boy may be slightly taller. So where is it, the kind of clothes that a girl wears versus what a boy does? So inadvertently, we have certain features that we store in our head, which makes us distinguish between two separate classes. So the primary stage of an object detection model is the feature extraction stage, wherein we use compute intensive operations to accurately capture whatever is present in that particular class of images, right? And you have multi-scale features. We'll come to what this multi-scale really is. And then we have something called a detector. The detector, what it does is then once it's given a new image, it's able to say that, okay, I have seen these features somewhere here in this particular area of the image, which I have learned before usually belongs to a girl or a boy or a cat or a dog. And then it recognizes that, it detects that, okay, this is probably what I am looking at, which is what we're teaching the model to do, which then gives us bounding boxes. So it tells you that, okay, in this region, this is what I see, and this, I think that it is a girl. So first of all, to identify that, yes, there is an object over there, and second, to say that I think this object belongs to this class, which is what happens, this is a nutshell of an object detection model. Coming back to YOLO v3. I will now introduce you to the concept of darknet 53. It's got darknet is essentially the feature extractor for version 3 of YOLO, which has 53 layers, right? So this looks very complicated, and it's usually something that we skip, even for many of us who've done machine learning projects in the past. But what this has been condensed into this diagram that you see over here, right? What is happening over here is that this entire block represents darknet, which is trying to extract features from your image. So you have images. Now, this brings us to the concept of filters. What do filters do? Filters are, they're like these little detectives that go all over your screen, that go all over your image, various sections of your image. And from each image, they try to extract what they think will be relevant in identifying your object, right? And the size this is in terms of pixel. So this is the size of the particular filter, right? Which is essentially how a convolutional neural net itself works, right? So you have a convolutional layer, then you have, so this entire block, let's look at this. You have convolutional downsampling, and then you have residual blocks. What are residual blocks? Residual blocks, as was introduced in the ResNet model that we saw, is essentially transferring of knowledge from layer to layer. So that the next layer is not learning from scratch, absolutely, but it's actually it has some amount of knowledge that gets transferred across the layers, which helps in identifying and reiterating the process. So the second time that I learn something, or the second time that I'm trying to do a particular task, I have a certain amount of knowledge from the previous layer. What we have also introduced are skip connections in between, so that I'm not completely biased by what I've learned in the past, but I do hold on to some information which improves my accuracy. So this is broadly how it's how it's structured. You have convolutional layers, you have convolutional downsampling, and a residual block. Multiple such blocks, which then gives us these three things: feature vectors of three different sizes: 52 cross 52, 26 cross 26, and 13 cross 13. Right. So this, So this is one of the big advantages of YOLO version 3 over the previous versions, is that we are sampling at three different scales. Right? So we are capturing features at three different sizes. This is one of the biggest advantages, which I have enumerated, which essentially is able to capture even objects that are extremely small. For example, one of the open problems right now is to develop a system that tries and detects whether a person is wearing a mask or not. Now that's going to be a very small portion of an image if you're taking an image of a very crowded lane, right? So a YOLO version 3, it samples at various sizes. Now, if I have to detect a person versus if I have to detect a mask of a person, it will be very different. So I'm extracting features at three different scales, right? So let's go over the points that I've just noted down on the side. So it's a fully convolutional neural net that performs object detection and localization. It's the darknet 53, two such layers attached. So it's a 106 layer FCNN. It uses regression to predict what I was talking about, the coordinates of the bounding boxes as well as the classes, right? It gives you a probability. And the shape of the kernel, this is kind of important, is 1 cross 1 cross B into 5 plus C. So here B is a number of bounding boxes on the feature map that a cell on the feature map can predict, right? And 5 is that, so we have 4 bounding box attributes, which is X, Y, H, and W, right? And the fifth attribute is the object confidence itself, that I'm this confident that this particular thing belongs to this, that there is an object. Sorry, there are two things. There is object confidence and there is class confidence. Object confidence being I'm this much confident that there is an object in the bounding box that I'm talking about. And class confidence is I'm Z confident that it belongs to this particular class. And C finally is the number of classes that we're handling, right? So now we saw these three inputs coming in from the previous diagram, right? We saw this. So this comes in as an input. So let's start here at the bottommost layer. You have these filters. I told you the kernel's running over the image. This is upsampled and concatenated with the next sampling layer, right? Which is then again upsampled and concatenated. And this finally goes through and we get three different kinds of outputs. You have a small scale, a medium scale, and a large scale output, right? So I think I've tried to give you like a basic overview of how exactly a YOLO V3 works. We can, of course, get into specifics of things like anchor boxes, etc., if we have time later on. And you can obviously ask doubts, but I'll just quickly run through the other sections, or the notes that I've noted down. So what we did is that we used darknet to train custom weights. Custom weights, why? Because we wanted the model to understand what really are the features of these two anomalies that we are dealing with, right? Darknet, one of the advantages is that it leverages CUDA. CUDA is the library that essentially helps YOLO run like a 500 times faster on like a GPU cluster. We will come to what a GPU cluster really is and how to use it, right? And this combination of YOLO V3, which uses darknet 53, it gives us a very good speed and accuracy for real-time detection. So like I told you earlier, YOLO V3 detects even smaller objects due to this concatenation that I am talking about. It is able to capture boxes at various scales, and it is 1,000 times faster. And when we have very compute intensive operations, 1,000 times faster is unimaginably faster than something like an RCNN, right? Because it is a single shot detector, like Soumya explained before. So this is something that's very important to us. And obviously we are able to detect, we're able to localize, we're able to classify with YOLO V3. I will also quickly tell you why for us, I keep saying that the accuracy is not as much as probably something like SSD, etc. Why is that not entirely such a bother to us right now? Is because if we're able to broadly say that, okay, there is this anomaly in the frame that we are seeing, right? It's this application is currently being used to tell the doctor that, okay, for a person sitting in a rural place, we have analyzed this endoscopic video and we feel that there are anomalies that are present, right? We're not actually performing the surgical procedure itself. So slight error in the localization is admissible to us as long as we are saying accurately that, okay, this anomaly is what this person has, right? Which is why, again, the YOLO V3. This is a comparison across models that we ran. And this is like a qualitative as well as a quantitative comparison. To my left, you have a quantitative. So the YOLO version 3, the faster RCNN, and this SSD, right? So so like you can see, the time for training, very, very different. The YOLO V3, time of prediction also much less. So the input image resolution, all of that remains the same. The loss. One important thing that I missed is how exactly loss is calculated for like something like a YOLO V3. It essentially is slightly different from all other traditional object detection models because it penalizes a couple of things. First being the objectness score, which I told you about earlier. That is, it penalizes that very heavily, where a bounding box wrongly says that there's an object here when there is no object at all. Second, it also penalizes the class probability scores. If there is a wrong class prediction, if there's a very high penalty parameter that is attached as compared to other models. And this is essential because we are doing detection as well as localization in one shot itself. So this penalty error is much, much higher, right? And one of the key advantages, like I told you, it can detect small size objects much better than other ones, and it detects three different scales, right? So you have over here comparison of YOLO V3 retina net 50 and retina net 101 versus other models. You have the MAP 50 as well as time. These things are something that Tejas will explain to you in his part. Now I'll come on to what the demo that I'm going to show you post this. So what really did we do? So first thing, we showed you our data sets. We collected and analyzed these GI endoscopic videos. We annotated them manually. We have a tool which we use to actually annotate these the frames extracted from these videos, and then the annotation that we did, we got it verified from authorized medical, from doctors and radiologists, and so yeah, we got it verified, and then we trained our own weights for the model using darknet. Like I told you earlier, this step is essential. So like while we say that the architecture of YOLO V3 is what we've used, the weights are custom. So our model knows how to detect a polyps or esophagitis. So that is something tomorrow. Like tomorrow, if y'all are training your own object detection models or training your own custom weights using GPU for the specific task that you take up will be essential, because then it will help you improve the accuracy of your prediction. So yes, and of course, as is every data science problem, we saved the trained weights. I will show you the checkpoint files that we generated when we reached minimum loss and high precision. Coming to our next point, I spoke earlier about darknet leveraging CUDA, which essentially runs on GPU clusters. So why did we use a GPU? Is because a GPU is a graphical processing unit, which is far more efficient as compared to a CPU. So what it does is that it does not transfer the entire operation to the GPU itself, but like you can see over here, the compute intensive functions are transferred to the GPU, and the sequential code, which can run really fast, is given to the CPU. So it essentially decouples these two things, processes them in parallel, and then finally gives you like a much faster output, and it vastly reduces your training time, etc. So you have open source things like Colab, which give you like a certain number of hours or certain number of computations of GPU itself. And of course, you have things like AWS and Azure, which you can use to, get a section of GPU to train specific models. Highly advised to reduce your training times and improve the quality of your model by running more epochs on it. Yeah, and I think that should be my last slide. So two more things. The data set that we've used for training and testing, this is a number of images just to show the authenticity of what we've done. Like we told you, Quasar dataset had 1,000 images per class. So we divided it into this rough ratio, 770 and 193 for polyp and 723 and 181 for esophagitis. A couple of images we had to discard because we ourselves weren't clear as to where the anomaly actually was. And the evaluation metrics that we used, we'll come to this in detail later on. Tejas will take it up. But broadly, we used the IOU, intersection over union. He will explain that to you. So this is a concept that's used both in the training of the model as well as in evaluation. So, I mean, yeah, it measures the overlap between what the actual boundary is and what the boundary that has been predicted. And, it penalizes that. And that is used as a threshold to, classify it as either true or false. So yes, this is a summary of exactly what I've told you. This entire first thing is how we developed our system, and this second thing is how we're going to what happens when a new image comes in and how we process it. So yes, we collected the endoscopic video. So this can be generalized to any video processing task that you can take up tomorrow. So you collect the video from this thing. We extract frames from it at a rate of about 25 frames per second. We do a manual annotation of anomalies and in that particular frames itself. The validation of the annotations is a very essential step so that you don't have erroneous results. We designed our vision object detection model, right? And we finally trained the object detection model. What we also did in parallel is that of the anomaly itself, we have a lot of images that we got from the EndoAbs dataset. We validated that they belong to that particular class as has been put out there, and a classification model, like we told you earlier, it's a deep learning based classification normal CNN model, and that we trained. So that combination of two things, object detection as well as the classification model, which have been combined to validate the results that we obtained. This model is what is passed over here. So video sequence comes, frame extraction, the model, anomaly detection, and then we give you the results which went into clinical trials. So I think I'll show you a quick demo, if that's okay. I think we've got disconnected. All right, okay, we're good. All right, so before I get into this specifically, let me show you the annotation tool. So any questions before that? We need some sort of feedback to know that it's going okay. Should we go faster, slower, anything? Kalbande sir, Rathod sir, all good? Okay. All right. So yeah, I will now show you the annotation tool. Yeah. So hopefully this should be a little more interesting, and you will be able to actually visualize and use this possibly in applications in the future. So you can see my screen, right? You can see the YOLO annotation tool on top. I'm hoping. Okay. I'm going to assume that's a yes. So what I have over here, okay, this is the directory from which I've run my script, and it's opened up this tool. I have this images folder inside which I have my two classes, polyps and esophagitis. So I go into polyps. Okay, where are my images? Okay, so you can see over here, esophagitis, my images are there. I don't know where my polyps images are. Anyway, let's, so I'm just using a couple of images just to show you. Here I specify my directory and I hit load. Okay, and like over here you see that within my directory, one by one, all the images get loaded. There's another thing over here called choose class. This is here, there are two different classes, esophagitis and polyps. Where does this come from? Is I have something called a classes.txt where I need to actually, in this file, I need to specify where, what my two classes actually are. So what we're doing over here is we're manually annotating the images and telling them that, okay, this image belongs to this particular class, right? So that's what we're doing. And now if I go into labels, so this is where my results are actually stored. So esophagitis, there is one result. I will delete it so that you can see, right? So this is empty. Once I create my annotations, I actually have results in that. So for example, let's say, so it's an easy drag and drop tool here. And to the right, you can see that my coordinates are actually generated. So my starting XY and my concluding XY. And this is the class to which it belongs. What I can also do is create multiple such bounding boxes within the same image, right? Or I can have a single one. And then I go to the next one. Over here on my terminal, you can see that it has said image number 1 is saved. And if you check my labels, so the name of the image is test4. I've generated a test4.txt, which actually has the information of these bounding boxes that I just created, right? Similarly, if I, okay, for example, let me get in a couple of polyps images so that it will be clearer. Okay. So here I specify my directory, I load my image, I change my class, and I actually draw the bounding box across it. So I can, like I told you before, I can draw multiple, I can draw overlapping, everything is allowed. So this is something, this helps actually solve this tool helps to solve one of the biggest problems that we face when it comes to like annotating the data. This is a fast, efficient annotation where you can actually see what you're doing, and you can just keep going from one image to the next, and you can create your bounding boxes, and your labels get generated immediately, right? So there are 3 scripts over here. The first one that I just ran, which is main.py. Then you have the check.py, which checks that, okay, all my labels and everything is generated in the correct format. And then finally, I have this script called process.py. So process.py, what it does is like it takes my annotations and it then, and like my image names, and then it kind of generates this train.txt and valid.txt where all my image names and as well as their annotation, the corresponding annotation files, the labels are all stored, right? And this is what then we give as an input as training data and valid and testing data to our model. So that's it. These 2 files are what goes to our model, and these are the entire process is completely automated, right? So yeah, like if I go next, I just like a quick demo. I will not dwell too much on this, right? Yeah, so you can see over here under polyps, 3 images were loaded. Number 1 and number 2 are saved, and um, in my labels is empty before. These are my files that get generated with the results stored in them. So this is my annotation tool. Now I will give you a demo of the next part. Now we have, we've got the annotations. After Tejas's results, we'll walk you through the entire part where it comes to how we train our model, etc. Just to keep the interest alive, I'm now going to show you a demo. I'm sorry. Yeah, there we go. So I'm now going to show you a demo wherein we are actually loading the model that we've already trained, and we're showing you how the annotations actually happen, right? So I'll just take you through those quick files. So over here, I have a couple of testing images, right? They're actually the same. They're some random images that I've selected. We don't know the class to which they belong. Okay, these are just random images that I've taken, and you can see them on the side. And I'm going to try and make a prediction on them. So I'm going to run this script main.py. What main.py does is it takes these 6 or 7 images, and then it gives you the bounding box as well as the class to which it belongs. You can also check out the latency over here. The predictions are made almost instantaneously. And I will show, and then this particular, it calls the get predictions API. The get predictions API comes from the script detect API function, which is a very detailed script. And over here, if you see, so this is my YOLO v3 custom.config. This is my configuration file, and this is my model itself. It's a very heavy model. So the YOLO version 3 checkpoint, right? That's the number of epochs that we have run it on, and that's how we've stored it. So over here, if you see under my config directory, you have my config file as well as you have the checkpoint, which is essentially loading the weights. And these are my classes that I'm predicting. So I will run the main.py function and check out here the latency. All right, this is how long it takes per image for the entire model to run and give you a prediction. That's how fast it is. So it's almost instantaneous that the files are processed and it generates the outputs. Yeah, so in my temp folder, in my outputs, let's check out the outputs, right? I will expand my screen so that you can see it. Yeah, there we go. So this is polyps. Very well. So this is the class, and this is the localization. So it's correctly detected that, okay, this is where the polyp is in the particular region. Similarly here, these are new images. The model has never seen these images before. We can actually test it on any random images. This is esophagitis for you. So over here, correctly, it's detected the red striations. The transition between normal and red is where it is telling you that, okay, here is where your esophagitis really is. So yeah, I'll just quickly show you the 6 images that we ran it on. Right, again, esophagitis. So this is normal, and this is very red striated region. Over here, you can see the gastric acid reflux that's happening. So a very interesting thing would be an end-to-end demo, right? Where I actually give a video and it's able to annotate it for you in real time, which I will do, but you'll have to wait a little longer. Right after we analyze the results of this entire section, we'll give you a live demo of how it's getting annotated in real time. This is just a demo of how each of the images get annotated and how long it takes. So again, polyp, right, and one more, last polyp. So yeah, and before I move on, I'll just quickly show you the data that we used to train on, and then I will hand it over to Tejas. So this is our sample data. So yeah, these are unannotated. Once we annotated them, we generated the labels, right? And then if I go back, I can show you my final I will show you the files in which we've actually stored the train.txt and the valid.txt. I think that's in another folder. I will show that to you in in the demo at the end of this session. So yeah, so now I think Tejas, you can take on from here.
Yeah, sure.
Okay.
Right. So moving on to the result, how we actually getting those annotated images, the predictions and find how our model is. So before I directly jump into what our results were, a step back and let's look at what model evaluation actually is. Basically how you numerically quantize your model, which question in the chat, any standard data set. Yeah, sir, we'll come back to that. I'm going to cover that. Is my voice breaking for everyone?
Yes, Tejas, your voice is breaking.
Okay. Just a second. Maybe that's what caused. Little better now.
Say complete sentence.
Okay, so let's move on to model evaluation. What is please?
Yeah,
please,
better. Continue.
Yeah. Okay. So model evaluation is essentially how you numerically quantize the results of any machine learning model that you have. And why is it required? Is A, because you don't really know how much predictions that you've made, how much are they correct, firstly, and secondly, if there is a number of models that you've trained, how would you justify which one is the best one out of them, or which one is most likely needs a little more improvement? So essentially, model evaluation is the key part which comes at the end of any machine learning pipeline, and it helps you to judge properly what the results are, and finally take a call on which models you want to put on production so that people can actually use it and it is deployable in the first instance. So that is what model evaluation is, and we've done that complete model evaluation for our project also. But before I tell you more about that, there are a few more deeper insight into how model evaluation takes place. Challenges in model evaluation. That essentially is the biggest drawback, not drawback, I would say a bottleneck in most of machine learning applications nowadays. And this is because as in when the machines are getting more intelligent, it is becoming more and more difficult to evaluate their intelligence. What I mean by this is that, let's say 1 decade ago, the machine learning domain was just into classification. Let's say, given an image, it would tell you whether it's a cat image or a dog image. So evaluation is easy, right? You can just look at the image and tell whether it's a cat or a dog. There isn't much of a intelligence that's involved just to evaluate it. Fast forward to right now, we have generative models which are even generating music from previously learned music, so that you can actually get something which is machine generated. So now, how will you evaluate whether the song that is generated by the machine, is it melodious, is it accustomed to the kind of music that you're listening to? So these kind of things, as we keep on progressing in machine learning, we keep on adding intelligence to our systems, and it becomes even difficult to evaluate how much that intelligence is on par with the human intelligence. And hence model evaluation is now become a very key aspect. Leading research laboratories that are into machine learning and stuff are actually doing research just on what model evaluation techniques are, because as and when we progress further, we might need better and better techniques to find out which the most robust model is. So that is the motivation behind this complete domain of model evaluation. And even in our scenario of object detection, which is, I mean, fairly in right now, it's been 4 to 5 years since this object detection domain has come into play, but we still find that we need better evaluation methods. That is uh, one of the findings that we found out from our research. So examples of model evaluation: regression, classification, detection, recommendation. So just to walk you through, this will actually validate the claim that I've just made, that it's getting difficult to evaluate. Regression means something that you look on the first figure on the top. You've got a lot of data points, you're trying to fit a line through it, and essentially what you want is that given any x, you can get the predicted y properly. So evaluating a regression is fairly easy, because you can look at the graph and say, okay, well, this straight line is covering all my points, so this is a better fit than other straight line or other curves, right? Similarly, with classification, in which you want to find out whether a given data points belongs to class A or class B, you essentially just look at the decision boundary and find out whether it is properly separable or not. For example, in the figure that you can see all the blue dots are easily separated from the green triangles. So yeah, uh, on the from the way it looks, yeah, it looks like a good model. And obviously, there are ways to evaluate it. There are numerical techniques to it, which are pretty robust right now. Now, moving on to object detection, which is the domain we are currently focusing on, you can see a sample result of object detection model. Not only do you need the correct labels that are assigned to each of the object, you also need to localize it correctly. I mean, you can't really put a box anywhere in the image and say, oh, this is a person. So to evaluate this, you not only need a proper classification module as you've seen earlier, you also need a proper localization module which will tell you exactly whether the predicted bounding box is actually matching the real image. So this actually shows you the complexity in how much evaluation we've just gone through in just these three uh, types of machine learning problems, which are actually very prevalent even nowadays. So as and when we go further, it might become difficult to bring out even more robust techniques. So finally, I'll just touch upon recommendation. Recommendation basically means let's say you bought pair of shoes on Amazon, and the third time you go to buy something, it shows you, okay, let's buy a pair of socks also. That's a recommendation engine. Let's say you have two recommendation engines. You've bought two pairs of shoes from Amazon. One tells you, okay, you can. The next time you go to buy, one model tells you, okay, why don't you buy a pair of socks? Whereas the other model, why don't you buy a fridge, let's say. So to me as a human, I would say, okay, model A is better because shoes and socks are related. If I've bought shoes, I might also need socks, but there is no relation between your shoes and a fridge, right? So As you can see, this involves a human to come into the picture and finally tell that, okay, shoes and socks are related, but shoes and fridge is not related. So this is the intelligence that has been programmed into the recommendation system. However, to evaluate that, we still need a person to uh, establish these relationships between the objects. You can't expect a machine to already know that, okay, uh, shoes and socks are related and not fridge is not related to, right? So again, the point I'm trying to make here is that even though machines have become intelligent, even to evaluate them, a human standard is the most robust way of doing that. And unless we're able to automate that part, where we actually lack a lot because we are not able to completely automate that, which which requires a decent amount of human efforts. I mean, you can't have a person sitting and for all the recommendation that Amazon makes for millions of customers, you can't have a engineer sitting there and telling, okay, this is the right recommendation, this is the wrong recommendation. You need evaluation metrics that can do that automatically for you and tell you that, okay, this model is not making good recommendations, we need a better model. So that's the main motivation behind the model evaluation part that we're looking into. So moving on to the next slide, I'll first introduce you to the common terminologies that are currently there uh, in this complete aspect of machine learning. And when it comes to ML, we talk about functions, right? We talk about what kind of parameters you put into your ML model. So just a brief on that. Your prediction labels, these are the labels that you assign to your uh, predicted input. So given an input, your model makes some predictions, that is your prediction labels. Your true labels are essentially what actually the data is. So essentially, you're trying to compare how closer is your prediction label to your true label. If it is the closest, that is your best machine learning model. And how do you get to know that? That is because of the error function. Error function helps you quantize the difference between your prediction and true labels. So essentially, if your error function is zero, it means your predictions are completely matching your ground truth, which means that you have a very good model in place. Loss function. So this is actually a very debated topic in machine learning. What is the difference between an error function and loss function? So a very widely accepted view is that error function is what is the difference between a prediction and truth labels. And a loss function is trying to emphasize the error, which means that if your error is let's say linear, but what you want your model to, what you make your loss function to be quadratic, it means that you're trying to expand your error, which means you're trying to convey to the model that, okay, I am not comfortable with even so much error. I want my error to be very less, because once you square it, it's going to become even higher, right? So that is essentially the main difference. Your loss function helps you emphasize or put a significance on how much you want to put weightage to your error function. Many a times we see that error and loss function is actually the same. It's linear, right? As in whatever is your error, it's directly propagated as loss. And that is also perfect. I mean, you don't want to add any extra bias to whether or not you want certain error to be extra emphasized upon. So that is a very common and a perfectly useful technique. And finally, we come up to the optimization. So your loss function is essentially a function which tells you how much loss your model is making. And if you minimize that loss, you will end up getting a better model. So that minimization is done by what is known as an optimization technique. And very common optimization techniques are gradient descent, backpropagation, which is a version of gradient descent. And yeah, those are the most common ones. There are plenty more out there. I can't cover all of those right now. So just I'm touching upon the main ones, right? So if you see the equation on the top right part of the screen, that is a sample loss function for a classification module, in which y is your predicted ypred is your predicted label, and just y is your actual label. So let's say we have a binary classification problem, 1-0 problem. In that case, when your y is 0, the first expression of your loss function becomes 0 itself, because it is multiplied by y, which is 0. And your loss essentially becomes minus log of 1 minus y. So yeah, so that is one way, just an example of how your loss function works. There are many such loss functions. For example, in regression, you use a mean squared error loss, which is because you're dealing with continuous variables. In classification, you're dealing with probabilities. So this is a more uh, useful loss function, which is known as the log likelihood loss function, right? Uh, and the parameters, coming to the parameters. Now, these are functions, right? Every function requires some parameters to operate on. So commonly used parameters in model evaluation are learning rate, which essentially is the number of steps you take towards your optimal uh, optima of the machine learning problem. And this itself is a very vast topic, how to set your learning rate, etc. But just a rule of thumb, if your learning rate is very small, you would take very small steps towards your optimization, which would mean that you would require a longer time to train your model and finally reach that sweet spot. You will reach that, of course, but it will take a lot of time. If your learning rate is high, it would mean that you would take larger steps towards optimizing your machine learning model. However, it's possible that you might just overshoot, which means if you have a loss which is positive, you might decrease it so much that it ends up becoming negative. And a loss is loss. You don't want it to be positive or negative, you want it to be minimum at zero. So that is essentially what your learning rate is, and tuning learning rate becomes a very essential part of any data scientist who work on real world problems. Um, Lambda is a term which is used for regularization. I'll talk about regularization in the coming slide, what it means. And activation functions are essentially functions that induce nonlinearity in your data. I think there was a session on activation functions also in this FDP program. So I assume that was very extensively covered. Activation basically adds non-linearity to the data that you have and helps you cover better data points. To look at the graph on the right, your loss essentially is expected to decrease as you move on, as you train your model more, and as you can see, your accuracy would eventually increase. So that is a textbook example of how model evaluation takes place. Moving on, data set and metrics. So data set, essentially you want some part of your data set to be used for training, you want some part to be used for testing, so that you can uh, know that how your model is performing on data that it has not seen previously. So that essentially is how you split your data set. Generally people do 80-20 split. Cross validation is a new technique which is put up just so that your training phase itself is also optimized. So what you do is that in your training set, you set aside certain number of data points which you would use as cross validation. So you just train on a part of your training set and evaluate your training performance on the cross validation set, and finally report the accuracy on your test set. So that's an even newer technique that is currently being used. And the metrics that are used, yeah, right. So this is a very interesting point. Accuracy, we all know, we say that we want accurate machine learning models. What do we mean by that? Do we mean accuracy or do we mean something else? So accuracy, if you see accuracy, it means how many correct predictions out of the total number of predictions. So that is basically what accuracy means. But if you dive a little more deeper, you will find something which is known as a confusion matrix. What is the confusion matrix? I've shown it on the figure to your right, which means that out of the actual class and out of the predicted class, positive would mean that my actual label was positive, but I'm now also predicting it as positive. So that's a good sign for my model. Positive negative would mean that essentially false negative. It would mean that actually my class is positive, but my machine learning model is predicting it as negative. So that is an error which is making. This is known as false negative. Similarly, false positive, similarly true negative. Where accuracy essentially is true positive plus true negative divided by sum of all these four numbers. The precision is true positive divided by true positive plus false positive, and recall, also known as sensitivity, is true positive divided by true positive plus false negative. What do these mean? Now these both are very important terms. Precision means that out of everything which is predicted as positive, how many of them are actually positive? And recall means, or sensitivity means, that out of everything which is actually positive, how many am I predicting as positive? Now, if you look at the different applications in healthcare, especially, Let's say your positive class is your cancer and your negative class is your non-cancer. So even if there is a cancer image, do you want to tell the patient that okay, you don't have cancer? So that would be a very critical failure of the model, because you're not able to predict whether if the disease is there and you're telling that okay, there is no disease, as compared to whether there is no disease and you're still telling there is a disease. That is to a certain extent acceptable, because at the end the patient would become more cautious. That's all. He would go to a doctor and again take a test and find out okay, it's negative. So essentially, what I'm trying to convey is that false negative errors are very critical failures when it comes to healthcare as compared to a false positive errors. Because if something is positive and you're telling that is negative, it could be a very critical failure for your model. So essentially, it means that your recall rate is what you want to tune even more as compared to your precision when it comes to certain applications like health. Obviously, you want both your precision recall to be high, and since that is what you aim, you come up with a metric known as an F1 score, which essentially is a harmonic mean of your precision and recall. So with a high F1 score, you're ensuring that precision recall is both high. So these metrics are better used than accuracy if since you want to deep dive into your model and how it looks like. Okay, let's move on to now. Let's move on to the next slide. Uh, yeah. So bias and variance. So I'm covering this all in detail because it will come in the upcoming slides how we evaluated a model. So bias and variance is essentially the difference between your training and testing accuracy. After you train your model, if you find your train accuracy is high, your test accuracy is high, then perfect. I mean, that's what you're looking for, isn't it? But generally, you don't see such cases too often. What you actually see is that your train accuracy might be high and your test accuracy is low, which means it isn't performing out there when you actually scale your model. So this is a typical case of high variance, which means that let's say consider the graph on the bottom left. Let's say the data points are shown as indicated, and the line that you fit through them is also shown. You can see the line is trying to cover every possible data point. The problem with this is that given a new data point, it can't generalize to that. What it has done is taken your train set and completely fit itself over it. So this means your train accuracy would obviously be high because I mean you're covering everything that's there in your data space. But your test accuracy will be low because given new points, it won't be able to perform that. So that is what is known as high variance, also known as overfitting, as suggested by the term, because you're overly fitting your data points. And this is tackled using regularization, which is a technique in which you penalize your functions, you penalize your weights that you're giving to each of the input functions. In contrast to this is high bias. What high bias means is that your train test accuracy is low given, but even your train accuracy is low. So this would mean that a model is not even able to learn from the features that it currently has. As it is shown in the second figure, you can see the data points are scattered and you're still trying to fit a linear line through it. And it is not able to cover all the data points. This is what is known as underfitting. And underfitting can only be tackled with a better modeling technique. You either improve your model, you either add more features to your model. That's the only way in which you can tackle high bias. So what we want our model, a good balance that is on the rightmost figure. We want it to fit it pretty smoothly so that it can not only generalize well, it can also learn from the current training data that it has. So that's the difference between high bias, high variance. What you essentially want is your model to have both the variance and bias to be low. You want to hit that sweet spot. So yeah, with this all prerequisite in mind, let's move on and evaluate how the current situation was. Correct. So coming back to our problem, the gastrointestinal problem that we had. So the data set that we used, someone had asked which data set that we're using. So the data set that we're using was Quasar data set, which is openly available. Uh, it has some 1000 images of esophagitis and polyps classes, and these are unlabeled images. All right. So the first thing that we did was, out of these 1000, pick out a few set of that, the numbers that Rithvika discussed, from which we were actually able to find out what the anomaly was. So that was the one thing that we did. And after that, the annotation tool which she showed, we used that tool to actually find out and localize the anomalies, prepare a training data set by ourselves. A few assumptions that you're making when we are diving into a results section. False negatives are more critical failures as compared to false positives. I discussed this point previously because we want our recall rate to be higher. We don't want to tell the patient, hey, who has a disease, that hey, you don't have a disease. That would be a much more critical failure to a model. So, having said that, we still want a reasonable trade-off. We don't want to overly optimize recall such that our precision becomes very low. And to do that, we have two important parameters that we consider, that we tune basically, which is the confidence threshold and the IOU threshold. I will discuss this in the next slide, what the confidence in IOU means. So essentially, confidence is inversely proportional to the false positive rate, and IO is inversely proportional to true positive rate. What it means, let's move on to the next slide, and I can show you a diagram in which you can easily make out what the confidence and IOU is. Right. So the leftmost figure, the black background, so you can see a few boxes and with a few percentages written alongside. So the green box is essentially what your true label is. That is, in a given image, your green box is essentially what you have annotated using your tool, and the red box is what your model is predicting, and that red comes with a percentage associated. So this is your confidence threshold. What happens in object detection models is that your model outputs a lot of such red boxes, some having percentage of 70, 80, some having as low as 10, 20. What this means is that the model is 10% sure that, okay, hey, there is an image, there is a target image in this particular box. Whereas as compared to 90% sure. So we set the confidence threshold such that if a threshold is 60%, it would mean anything which is less than 60 will directly discard this prediction, because we are confident that the model is not sure that there are any detections there. So hence that helps you tune your model to a certain extent. And IOU, as shown in the right side figure, it is the intersection over union. It's a fraction. So you have B1, B2 as your original and predicted boxes, and your intersection is the intersection of the two boxes. Union is the union of these two boxes. So if your IOU is 1, it would mean that you have a perfect match. The predicted and true box are matching perfectly. If the IOU is very low, it would mean that your union is very high and your intersection is very small. So hence, low IOU would mean that, okay, it's not a good prediction. So by setting this IOU threshold, you also can filter out a few false detections and evaluate your model even better. So looking at using these two, let's go to the next slide and decide uh, how we used. So yeah, before that, these are a few of the test images that we also showed earlier. As you can see, in esophagitis, we are able to mark these boundaries on the anomaly. One key aspect to note here is that esophagitis is irregular. So this means that essentially we're trying to it is not circle, it is not square. It is something which is just spread out on the walls of the esophagus. So we are not having a square bounding box is not the most accurate metric that we are choosing. And we've proved that mathematically. And that is one of the key research gaps that we are trying to fix also. So that was one key observation that you need to make in esophagus. But in polyps, if you say, polyps is a regular shaped anomaly, like you can see in these figures. So it's a circle which can be pretty accurately covered by the square bounding box. Sorry. Yeah, so by the square bounding box. Yeah, coming to the training phase, training comprised of 723 images, esophagitis 730 polyps in images. So we use TensorBoard as a tool to plot these curves, and you can see the loss function is constantly decreasing. So this indicates that, okay, the training is actually going on pretty well, because as in when you train your model function, you want your loss function to decrease. At the same time, precision recall is increasing also, so which would mean that yeah, the model is learning well. So training phase was pretty good, and that was also indicated by the accuracy figures that we have in the next slide, which indicate that training phase, uh, we really performed well on the training phase. We'll move on to the next slide. Right. So what you can see in the table is your uh, AP essentially means your average precision. You use average precision to measure your performance of any object detection model. And IOU and confidence parameters I discussed earlier, we use those to tune our results. So you can see that with decreasing IOU, as you keep on lowering your IOU, your precision of both the classes will increase, because it means that even with a low IOU fraction, you still want to make a correct prediction, right? So as you go on decreasing, it would uh, keep on increasing up to an extent after which you can't really increase your true positives just by decreasing IOU. You need your model to be more robust to include that. So that sweet spot was 0.4, as indicated on the green highlighted line in the table. And with the confidence parameter of 0.8, we got almost 90% accuracy on esophagus, 97% on polyps. So that's close to 94% model accuracy, which was really good for the training phase. And after that, it flattens out eventually. So if you can see below the green highlighted row in the table, 0.9, 91, 91, 98. So you aren't able to make significant gains even after decreasing IOU after a certain threshold. So that is a threshold you set to quantize your image, quantize your results, and that was 0.4 and 0.8 for us. Coming to the testing phase, we found some really interesting results there. So we have a similar table for the testing phase too, in which, right. So the assumption that I made, that after decreasing IOU, the precision keeps on flattening. That's true for polyps, because after 0.3 you can see 70%, 74, 75, not more than that, right? But for esophagus, the precision keeps on increasing, which means that it has still yet to reach that sweet spot after which we can stop decreasing our IOU. So this essentially confirmed our earlier assumption that IOU was not actually a correct metric to be used to evaluate esophagitis. And that is because esophagitis is an irregular shaped gland. You can't use a square bounding box to accurately measure something which is irregular. Right. And hence that's the key research gap that we identify, that even after reducing IOU to such a small extent, even to 0.01, we are not able to stabilize esophagitis, which meant even though we are not able to prove the results, even though you saw in the testing images that I showed you that the boxes were pretty accurate. We were able to capture a large part of the anomaly. It's just that mathematically we are not able to justify that because IOU isn't the best metric, right? And yeah, so circle bounding boxes are not actually acceptable in the YOLO method. That is because YOLO only works on square or rectangle bounding boxes. So essentially it takes in four parameters, which is the x and y of the starting coordinate of the rectangle and the length and breadth. So only those four parameters are used to make that prediction. Hence, circle is not used in YOLO technique. In fact, that is something which we thought of as a new research improvement on the current evaluation metric. That why not change the complete method of annotation, or change the method of evaluation in which you don't use that square bounding boxes, so that you can improve these figures that you're looking at, right? So we have a few graphs in the next slide that will just validate the assumptions that we are telling you. So if you look at the first Okay, we'll first look at the second graph of polyps on the test set. You can see as you move from left to right, almost from 0.0 to 0.5, your values are pretty much stable. After that, they take a deep dive because obviously, if you just increase your IOU threshold to a very large extent, you will get very few true positive predictions. But if you see for esophagitis, even from that 0.0 to 0.5 range, your the metric is actually falling a pretty large, pretty with a pretty large margin. It's not stable essentially. So this just reiterates my earlier point that IOU was not able to perfectly stabilize esophagitis because it's irregular. Whereas we can see a good enough prediction accuracy because it's regular and the square could properly fit the anomaly. So yeah, so overall, moving from the discussion that I had earlier, we can say that the model has high variance because it's performing very well on test set. It's also performing very on train set. It's also performing very well on polyps test set. Polyps esophagitis test set. It is performing well, but we're not able to mathematically justify results just because the metric doesn't exist right now. So that was the key identifying research gap that we made. And concluding, uh, maybe before concluding, we could just show the demo, the video demo that we had.
Sure. So
Yeah, the benchmarking data set that is there was the Corsair data set that we had. We used that for our use. And apart from that, there is a COCO dataset which is widely used for any object detection model. So even that can be used for any sort of benchmarking that is to be done.
right. Thanks, Tejas. So I'll just quickly show you two demos that we made like in real time of both esophagitis as well as polyps. These are just random videos taken off the internet of live endoscopic procedures. And yeah, so here goes. So you can actually, just started. So this is, you can see the scope actually moving inside and the frames being captured and they're getting annotated in real time. You see the striations being created and the bounding boxes are actually defining the anomaly into that particular region. And they're identifying them as esophagitis and localizing it to that where the striations exist. So, right, this is about a 30-second video. So over here, I mean, say for example, we have someone trained medical people performing these procedures in rural hospitals. They need not be specialized doctors. And then you have something where in real time, this product actually, annotates it for you and tells you that, okay, this is the anomaly that you possibly have. And it is then relayed to, a doctor, and a doctor can look into it and, what really has to be done. So that's essentially the application that we're chasing, and we just enumerated to you how we've gone about solving this problem. So over here, you see an interesting fact is that it's able to detect multiple anomalies, like on one single frame. So again, it's at the rate of 25 frames per second that you see aggregated together. And so it's able to actually localize so many different polyps in a particular region itself. And these frames, the bounding boxes actually overlap with each other as well. So multiple overlap, and there are some frames, like you saw in esophagitis also earlier, where there is no anomaly detected in some frames at all, right? So that shows the power of this over traditional CNN techniques, wherein it classifies an object into one of the X classes that you give it. It's never able to say that, you know what, this is not there at all. So that's another big advantage that is there. And of course, over here you can see the latency. There is hardly any. There is a slight pause that comes about, but it's mostly pretty quick and to handle the kind of real time annotation that we require. So yeah. Let's just go back to our conclusion. Then let's take questions. And if you want like a code walkthrough, we could do that.
Right. So yeah, so as you could see from the video that we had, we are making more accurate detection. We have good localization of the anomaly. You could see that the localization was better on polyps because it's a regular class as compared to esophagitis, which was a little irregular shaped. Since we are using IOU metric, we are getting those lower scores for esophagitis. And we really emphasize the need for having a better metric for such irregular shape classes using YOLO technique. I mean, in other techniques like RCNN, you have a pixel-based approach, but then those approaches are very slow. We used YOLO because YOLO is real time. You can actually deploy it. You could see the video. In real time, it was generating those frames. Such things are very difficult to achieve using something like RCNN, which is pixel-based. So we need an evaluation metric which is suitable for irregular shaped and works on YOLO. So that is a conclusion that we drew from all our results that we had. And yeah, that's about it. We could take any questions if anyone has any questions.
Any questions, please? No, I don't think, because you already answered, Tejas. The questions from the chat box, I think you already answered.
Right, yeah, yeah.
No questions? Okay. So everything done, Tejas, from your side? Presentation over, right?
Right. I mean, we could show a code walkthrough if that's required.
No, if there's a request, then we will do that. Otherwise, it's okay. For me, it is okay.
Okay, sir.
If anybody wants, students are interested, they are interested to show you code also if you anybody wants to see. Otherwise, it's okay. So I will do no request. Okay. So I'm going to summarize now here. Tejas, Rithvika, Soumya, great ending of our FDP program. And let me first share my screen, something that I wanted to share to you. First, accept you. First, you accept this one. These are our virtual mementos. You can see it, Tejas, right?
Yeah, sir. Yeah, sir. It's visible.
Yeah, this is virtual memento for Tejas. This is for Soumya. Soumya?
Yes, sir. Thank you so much. It's visible.
Yeah. This is for Rithvika.
Thank you so much, sir.
Yeah. I always say that the brand name of an institution is not because of the walls. It's not because of the how many classrooms or laboratories, air-conditioned laboratories you have, or how fantastic the building is. It is not because of that. It is because of the living bodies that are present in that building. So one is faculty and another is obviously student, right? Any brand name of any institution is only because of the students and faculty members. And I believe that after seeing this presentation, those who are attending at least today's session, they will definitely agree with me that S.P.I.T name is because of the students like you. It is because of the students like Tejas, Rithvika, Soumya, very great work. And I don't think that this is a BE project. People might say that this is kind of a PhD work, but then you are so passionate, you carried on this project. Means it is a kind of your intellectual property. You thought that you own this project, and that is the difference. Otherwise, what students do, एक project करना है करके, they do something and then they run away. It's not like that. After graduation also, you still remember your project, each and everything from the project, and you demonstrated in a fantastic manner. In fact, Tejas have summarized everything. Means he started from all the basic things. He in fact explained what is regression, classification on one slide, everything. And then entire model evaluation, how to do the model evaluation in 2-3 slides, which probably we are learning from so many sessions. And he has summarized it. So Tejas, great work. You have summarized how to evaluate the model. In short, in 10-15 minutes, you have summarized everything actually. You have actually summarized our FDP program, you know that. And in your entire 2-hour session, you three guys have used all kinds of keywords that we are using from last 15 days. सब यूज कर लिया आपने, सब सब I was very patiently hearing, and thanks for this session. I can only say now, awesome session.
Thank you, sir.
Very good, very good. I appreciate, and in fact, looking forward for many more inputs. And I know you are our student, so you will immediately agree. You will never say no, right?
Yes, sir, definitely. Looking
Yes,
forward to it.
Yeah. In fact, Rithvika is at Reliance Jio, right? Soumya, Piramal Pharma, Tejas, Miko. I think I would say that you might be very happy when they came for your placements and ये company मिला ऐसा वैसा. But it is a vice versa actually. You are an asset for that company. You know, आप लोगों company का asset हो. They are lucky that you people are there. I think so. This is my opinion. At least after going through this presentation, I'm 100% confident about it. Right? So thanks a lot. Thank you very much.
Thank
Thank you
Okay.
so much, sir, for inviting us.
Yeah. Now I'll only tell to our participants, those who are there listening. So tomorrow we are having the validatory session, as usual, you know. So this time we are not having so many things for validatory, but then morning examination is compulsory for everybody. Please appear for the examination, and it is must. You have to appear for the examination. It is open from 8 o'clock to 11 o'clock. In between this time, any point of time you can log in. It's a 1 hour objective type paper. Please do not log in at 10:45 and tell me कि sir 15 minute extension करके दो. That happens in every STTP FDP program. Please do not ask, at least in the last program. जो कर रहे हैं उनको मैं बोल रहा हूँ, जो करते हैं regularly. So at least you appear for 1 hour examination, and then we will start validatory at 2 o'clock. So immediately we will start with the session from Dr. Pari, Shiva Pari, who will be talking on managerial applications of data analytics. How to use data analytics in management. That is his talk. So as compared to our earlier FDP validatory sessions, this is a technical aspect. Okay, it is a proper session for us for this FDP. So he will be talking for at least for 45 minutes, and then we will conclude with our validatory function. Okay, so please join at 2 p.m. Do not forget to join at 2 p.m. And thank you very much. Thanks a lot. Kalwandi sir, are you there? Okay. Okay, thanks.
Thank you.
Thank you, sir. Thank you very much. So, thanks, Rithvika, Soumya, and Tejas. I'm going to end this meeting. Okay. Thanks a lot.
Thank you.
you.
Thank you.
Okay.